And we're just gonna give a few minutes to
Yeah, for sure.
our participants to just log in. If they're running inside after hail and rain.
Okay, so the hail is downtown right now. So yeah, not good for vehicles or just being hit by the hail.
Yeah, no, not nice at all. Yeah, here in Heritage stopped a little bit. There's a little bit of rain, that's it, but no more hail. That's good.
Well, at least it's not snow, so I'm happy about that.
Yes, me too. I agree. I agree. Okay, so we're gonna just leave more people to log in the meantime, and I'll just go and start with the introduction. And well, good evening, everyone. Has been a good day so far, even though we had hail and rain. So interesting weather here in Prince George. So I want to thank you for joining us tonight for our virtual adult speakers series. And my name is Carlos Hernandez. I'm the manager of in-person community programs here at the Exploration Place Museum and Science Center. We're located in Prince George, BC, and honored to live and work here on the traditional territory of the Lheidli First Nations people. I would also like to thank our media sponsor, CBC Daybreak North, for supporting this series. Also, at the bottom of your screen, you'll see a Q&A speech bubble. Please post your questions there. And we're gonna do it a little bit differently today. So you can do it at the end of the presentation or while the presentation is on. So you can do that and while the presentation is going. And I would like to welcome Stephen Déry. Stephen Déry is a professor in the Department of Geography, Earth and Environmental Sciences, and in the Natural Resources and Environmental Studies graduate program at the University of Northern British Columbia, which is UNBC. And he investigates the consequences of climate change and water management on the water cycle of northern and alpine regions. And again, thank you so much for joining us tonight. And now we'll pass things over to you, Stephen.
Okay, thank you so much for the introduction, Carlos. Really appreciate it. So may I share my screen now? I presume I can.
Yes.
Okay. Okay, so hopefully everybody can actually see that. And my slides start off with the title of my presentation, which is Rivers in the Sky, Unraveling the Atmospheric River Phenomenon. And it's probably a term that everybody knows now, unfortunately, because of the events of November 2021 in southwestern BC. So I'll be talking about some of the research we've done at UNBC on this phenomenon, go through a bit of an introduction in terms of defining what atmospheric rivers are. I'll talk a little bit about a field campaign that we had as well in the fall of 2021 in the upper Nechako. And I'll conclude with some ongoing research as well as looking into the future with climate change. So I am presenting today from the campus of UNBC in Prince George on the unceded and traditional territory of the Lheidli, which I wish to acknowledge. And the photo that you see is actually of the Tatsa Ranges and Tatsa Lake, which is part of the Lada Carrier 10 First Nation traditional territory. And that was part of our field campaign in the area in the upper Nechako, so beautiful area to do some field work. So thanks again for the invitation to do the presentation today. I'm really excited about this. And if you do see anything that's not clear or wish to ask a question as I'm going through the presentation, feel free to stop me. So here's the outline for my presentation. I'll go through the definition, the structure, and the evolution of atmospheric rivers. And we like to use acronyms in research. So you might see AR or ARS. That means atmospheric river, or the plural atmospheric rivers, just to abbreviate that term. I'll go through some of the research we've done looking at Well, how frequently do these storms actually affect British Columbia? So climatology of these events will look at their role in replenishing water resources across the province, go through a few exceptional AR cases, including the November 2021 event in southwestern BC. Then I'll move on to our field campaign, the Tatso Ranges Atmospheric River Experimental Trayer. Look at ongoing and future research we're doing at UNBC on this topic, and then prospects for the future. So here's a satellite image showing very clearly an atmospheric river. So we call them rivers in the sky because they actually look like rivers, but obviously in the atmosphere. And they're essentially composed of water vapor. So we have a lot of moisture in the atmosphere. And at times, some of this moisture, which a lot of it evaporates from the Pacific Ocean, for instance, will be essentially transported from tropical regions near the equator and then move from southwest towards the northeast and then eventually hit the coast of, say, California or other parts of North America like BC. So they contain a lot of moisture, and I guess the defining aspects of this is their length. They have to be about 2,000 kilometers in length, but narrow. So about 1,000 kilometers or less in width. And they have to contain a certain amount of moisture or water vapor to actually be defined an atmospheric river. So I'll go through a little bit more precisely that definition in just a couple of slides. Well, in our region, they're also known as the Pineapple Express. So it's a bit of a moniker that you might hear. And why are they called Pineapple Express? Well, if you look at this image, you see the Hawaiian Islands, and perhaps you will see my mouse here at the bottom left of the image. And we have a satellite representation of an atmospheric river. And they're just called Pineapple Express because the moisture often originates near the Hawaiian Islands. So of course, famous for its pineapples. And these pineapples transport not pineapples, but a lot of moisture, again, in this case, towards the coast of California, as you see with the arrow. Okay, so a bit of a technical diagram. I apologize for this, but I think it's useful to have a precise definition of an atmospheric river. So we see, this is sort of a map, a weather map, if you like. And we have L defining essentially the center of a low pressure system. So you might see a weather map like this on the web or in a newspaper, and associated with that low pressure would be fronts. Towards this plume of moisture depicted by the colors, we have a warm front. Intersecting that warm front is a cold front, and a line in front and along the cold front is that plume of moisture that we call the atmospheric river. And we use a term called integrated water vapor transport to essentially compute the amount of moisture that is being transported, in this case by this atmospheric river associated with a mid-latitude storm. Now the gray area has essentially water vapor content or transport that surpasses 250 kilograms of water per meter width each second. So that's a lot of moisture. And as you see by the arrow, it's being transported essentially in this case from the southwest towards the northeast. And then in orange is an area of higher moisture content. And then in red, which is essentially the center of that plume of moisture, has a value of 650 to 850 kilograms per meter per second. And in this case, this is being advected with the winds, and obviously can intersect essentially the continent and bring a lot of moisture that can cause precipitation. So last fall, we actually did some videography in terms of trying to explain this phenomenon. And so there's a link here. And if you do a search on what are atmospheric rivers UNBC, you'll probably be able to actually find the link and hear a little bit more about the definition of atmospheric rivers. Again, if these carry a lot of moisture in the form of water vapor, then there's a potential for precipitation. For precipitation to occur, we need rising motion in the atmosphere, just as we're experiencing in Prince George right now. We need some ascent, and in North America, we have mountain chains along the West Coast. And so that includes the Sierra Nevada in California. So you can imagine that plume moisture intersecting that topography, and it has to rise. And when it rises, it cools, the water vapor can condense into liquid water form clouds, eventually precipitation. If it's cold enough, that can be snow, but otherwise that can be rain, and it can be a lot of it just because there's so much moisture in these atmospheric rivers. In fact, these atmospheric rivers can carry as much water as the Mississippi, even the Amazon River, and sometimes multiple times the volume of those rivers. So they do carry a lot of moisture. Now on the lee side, so as the winds come down the mountains, they tend to dry off because they've essentially lost all their moisture. And that can actually cause what we call downsloping winds. And in the lee of the Rockies, we would call those Chinook winds as well. And because of their subtropical, if not tropical origins, they tend to be warm systems. They tend to bring warmer than average temperatures as well. Okay, so this is a bit of an animation that I've taken from the National Oceanic and Atmospheric Administration, or NOAA. And it shows essentially the integrated water vapor. So this is not multiplying the integrated water vapor by the wind, as we talked a little bit earlier, but just the amount of water if you were to condense that moisture as a column in centimeters. So the blue indicates dry air. You see that towards the north. We have Alaska at the top of the map, BC here, and then California down to the right of the map. And then the orange, the red, and then the purple colors indicate very high moisture content in the atmosphere. So as we move towards the south, we're approaching the equator. Obviously, the sea surface temperatures are very warm. There's plenty of moisture to evaporate, but you do see that the moisture tends to go from east, the right of the image, towards left. Now, at times, the mid-latitude cyclones are able to tap into that moisture, and you see these plumes actually being evected from the southwest. You can see the Hawaiian Islands right here towards the coast of California, even BC. And so these plumes of moisture are dynamic, and they're, again, elongated from southwest to northeast, but narrow, and then can transport that moisture towards the continent where it can cause a lot of precipitation. So we do see in this animation one atmospheric river that kind of follows down the coast, and then on the left side, you see another atmospheric river that is about to form and is essentially being transported from the west towards the east and will eventually make landfall in North America. All right, so any questions on that before we move on to the climatology of atmospheric rivers? So we've had quite a bit of work done actually on the topic of atmospheric rivers, starting with a PhD student, Asim Sharma, who actually defended in 2020 and was looking essentially at the climatology of landfalling atmospheric rivers across the British Columbia coast, as well as southeastern Alaska. The period of study was 1948 and 2016. And apologize, this is a bit of a complicated plot, but it's what we call a box and whisker plot. And the advantage of using this type of plot is that it can represent a whole lot of statistics on the distribution of, in this case, the frequency of atmospheric rivers making landfall each month. So on the x-axis, you do see the months of the year. The vertical axis represents a number of landfalling atmospheric rivers. Essentially, this is an atmospheric river that crosses the coastline. And the dots, the white dots that you see in the boxes indicate the average each month. Horizontal black line, the median each month, or the middle value of the distribution. The gray box is the interquartile range. The vertical black lines, the entire range, except the outliers, which are indicated by black dots. So what's important, let's just focus on the average statistics, the white dots in the boxes. And we can start in January, we see about 3 events on average each year. And that falls to about 2 for the months of February, March, April into May and June. Then we see that increasing. The maximum number of events is actually in September and October, where across BC and southeastern Alaska, we might see about 5 events each year. But that can vary from a couple, maybe 8 in a given year in 1 month. And then that falls back again in November and into December. So the busiest months for BC and southeastern Alaska are really September and October. Well, the other question that Asim asked was, are there changes over time? Are we seeing climate change impacts on the number of atmospheric rivers making landfall in British Columbia? And here he separated the domain into a lower latitudinal band, that's the blue curve. So 47 degrees north up to 53.5 degrees north. So just a little bit south of Prince George. And then above that, 53.5 to 60 degrees north. The blue line, again, indicates the number of landfalling atmospheric rivers in that lower latitudinal band from 1948 to 2016. And then the red, a similar plot, but just for the higher latitudinal band. You do see that at the lower latitudes, we do see more storms. It's stormier, more atmospheric rivers. We're closer to the tropics, the origin of the moisture, whereas the northern latitudinal band, we see fewer events, maybe 15 or so each year. Overall, over the period 1948 to 2016, the dash black lines indicate the linear trends, and we don't see a change. But if we focus on 1979 to 2016, we do see an increase, particularly at the lower latitudinal band. And in fact, the analysis showed that between 1979 and 2016, we saw a 20% increase in AR frequency. So a significant amount of atmospheric rivers in terms of an increase between those periods of 1979 and 2016. Okay, so the next few slides are maps. This is intended to show that atmospheric rivers are particularly important for replenishing water resources. Now, we hear atmospheric rivers when they're associated with natural hazards, as we saw in November 2021, but they're also important in the hydrological cycle, and in particular along the coast of British Columbia and southeastern Alaska. So here he was able to look at the contribution of atmospheric rivers to annual precipitation. Now focus on 1979 to 2012. And the scale is a percentage starting at less than 5% in the yellow. So you see that in northeastern British Columbia, we're far away from the Pacific Ocean and we're to the north, so less of an influence of atmospheric rivers. But as we move towards the coast, that ratio increases. And in fact, regions like Haida Gwaii, Vancouver Island, and along the coastal regions of BC, we can see up to a third of the precipitation annually that is due to atmospheric rivers. So particularly important actually for western parts of the province. And that includes southeastern Alaska as well. What about extreme precipitation? So here, he was just focusing on the one day of the year that had the highest accumulation of precipitation at each location in British Columbia, and seeing if that was related to an atmospheric river that made landfall along the coast of British Columbia or southeastern Alaska. And now the percentage scale you see has increased. So we have regions less than 10% in northeastern British Columbia into some of the interior valleys. But now along the coastline, the extreme precipitation event, again, the one-day maximum each year, can be due up to 90% of the time due to atmospheric rivers. So very important in terms of the extremes, the very high precipitation events that we can experience in our province. Okay, so I do want to mention here that the work that ASEEM did was part of a Mountain Water Futures program of research supported by the Global Water Futures Program, as well as UNBC. And his major chapters have been published in journals, including the International Journal of Climatology, Journal of Geophysical Research, and Journal of Hydrometeorology. So if you'd like more details on his results, I can provide you with the literature, of course, or his thesis, which is, of course, archived at UNBC. So the final part of his thesis was actually focusing on the land surface hydrology. How do rivers respond to landfalling atmospheric rivers? So he used a network of hydrometric gauges, 168 in total. This is across British Columbia and southeastern Alaska. These are operated by a Water Survey of Canada. And now he's trying to quantify how much of the runoff in a given year is actually associated possibly with atmospheric rivers. I have a couple of more maps here and then move on to some of the extreme events in BC on atmospheric rivers. So here we have the circles indicated those 168 hydrometric gauges. We have the contribution to annual runoff as a percentage. The larger the circle, the greater the percentage, up to 30%. And the smaller circle is less than 5%. So very similar to the pattern of the precipitation as we move towards the northeast and see less of a contribution of atmospheric rivers. The interior part of the province, including the Fraser, we have values maybe 10 up to 20%. And as we move towards the coast, well, we know we have a lot more atmospheric rivers, so the percentage can actually reach up to 30%. Particularly on Vancouver Island, the lower mainland that you see down here, and then Haida Gwaii. So again, important to consider atmospheric rivers in the land surface hydrology of British Columbia and southeastern Alaska. Again, looking at extremes. Well, now we're just looking at the major hydrological events each year and tying that to atmospheric rivers. And we do see that along, again, the coast of British Columbia into Vancouver Island, Haida Gwaii, southeastern Alaska, can have the extreme hydrological event up to 90% associated with atmospheric rivers. So again, this is just to illustrate the importance of these events in the water cycle of British Columbia. All right, so the next couple of slides are just to go over some of the major events that have occurred in British Columbia. Again, atmospheric rivers occur frequently in British Columbia, and in fact, we get about 35 events annually, but not all of them are intense. They do bring precipitation and often replenish water resources, but in extreme situations, they can actually cause a lot of damage and flooding. So you're all familiar now with the November 2021 Southern BC floods, where in Hope, BC, for instance, over 2 days, the 14th and 15th of November, we saw 277.5 millimeters of rain. So very large amount of precipitation in 2 days. Just recall, Prince George, here annually, we get about 600 millimeters of precipitation. So that's a huge amount in 2 days. Before that, we had in February 2015, huge amount of snow that fell in the Kitimat Terrace region in February of that year. And we saw up to 2 meters of accumulation that was associated with that river. And that led to some spring floods in that region and as well as in the Nechako watershed. And before that, we had the Bella Coola floods in September of that year, 2010, where we saw 250 millimeters of rain, again, over 2 days, causing $45 million in damages. And in terms of the precipitation, this was a 1 in 200 year event. So unfortunately, atmospheric rivers can cause a lot of damage. And ASEEM, as part of his work at UNBC, estimated that essentially between 1979 and 2016, atmospheric rivers that caused $500 million in damages. Now that's going to be superseded by the November 2021 floods. And the last estimate I'd seen was perhaps $9 billion in damages from that flood event. So obviously just horrendous situation that arose in November 2021 might be the costliest natural disaster in Canadian history. So just a map of the precipitation accumulation that occurred during that event in November 2021. This is taken from a paper by Nathan Gillette. It's submitted, I believe, at Weather and Climate Extremes. I'm not sure if it's published yet. I've seen a preprint. But you see there is an inset map at the bottom right showing British Columbia, and the black square represents the region on the main map here. So at the center of the map is Vancouver. This is the lower mainland, the lower Fraser Valley. This is Vancouver Island. We have northern Washington state up here. The circles indicate precipitation gauging stations, and then the color indicate the precipitation accumulation. This is derived from a reanalysis data set that essentially covers the entire portion of the study domain. So as you move from the cold colors in blue towards the hotter colors in red, we have higher precipitation accumulation. And it's pretty obvious that the mountains, North Shore Mountains, saw a massive amount of precipitation here. And in some areas, perhaps as much as 400 millimeters of rain. So this is towards Harrison Springs on the North Shore Mountains. Of course, just down here, the Sumas Valley that got essentially flooded. We have the region around Hope here that saw maybe 300 to 400 millimeters. But also important to say that the western part of Vancouver Island, west of Victoria, also saw a huge amount of precipitation, some regions 300 millimeters or more, and then northern Washington as well. And of course, the Nooksack Valley was also flooded during that event. Now, this event was exceptional in several aspects. So one aspect was that there was also a lot of snow already in the mountainous terrain, like on the North Shore Mountains. And because the air that was being advected was from the southwest, well, that melted along the snow. So that added to the runoff that was being generated from essentially the precipitation, the rain on snow. So that really compounded the flooding, particularly in the lower mainland. And as well, we did not have just one atmospheric river, but we had two back-to-back atmospheric rivers that made landfall. On top of that, the orientation of that plume of moisture was essentially almost parallel to the lower Fraser Valley. So that allowed the moisture to infiltrate inland, actually intersect the North Shore Mountains, the coast mountains, and lead to that orographic enhancement of the precipitation. And even before that, we had a major, actually a busy fall storm season, you will recall. So there was a lot of moisture already in the soil. Again, that was sort of preconditioning the floods that occurred in November 2021. So very catastrophic situation that arose from a combination of events. It was not just all the precipitation that fell, but the precursor events, the snow that melted, and the persistence of the event. Essentially, there was moisture infiltrating into the lower mainland for 3 days, causing all of that precipitation. All right, so we've been interested in this phenomenon since about 2015, and we have a program of research. It's a 5-year program of research supported by Rio Tinto and the Natural Sciences and Engineering Research Council of Canada for an industrial research chair. And part of that program of research was dedicated to studying atmospheric rivers. We had a major field campaign last fall called the Tatsa Ranges Atmospheric River Experiment, or TRAIR, and it was essentially focused on this phenomenon. We were also looking at other storms. And we're based essentially at Huckleberry Mine, as well as in the Medina Lake Lodge. And you see pictures of some of the equipment that we had. So the center image is actually at Huckleberry Mine. And in terms of the equipment that we had a hot plate to measure precipitation. Essentially, it's a device that evaporates any precipitation that falls onto it. And from that, you can estimate the precipitation rate. We had a small microwave radar. We had actually 4 of these at different sites. This is like a mini Doppler weather radar, except it points vertically only, but it gives you essentially some information on the cloud structure and the amount of precipitation aloft, and that's falling towards the ground. We had a laser disrometer. Actually, we had 4 again at several sites. This gives you information on the size distribution of raindrops or snowflakes, as well as their fall speed. We had weather stations. We were launching weather balloons as well to capture a vertical profile of air temperature, humidity, wind speeds, pressure. And we were taking some hydrological measurements, as you see on the left, with a device called the flow tracker to measure discharge. But we also were monitoring water levels automatically and water temperature. So we were in the upper Nechako for 2 months in September and October. The reasons we chose those 2 months was because of the work that Asim had done, showing that those were 2 busiest months for landfalling atmospheric rivers. So the objectives for a field campaign: tracking atmospheric and terrestrial pathways of storm-generated precipitation in the upper Nechako watershed, understanding precipitation formation, distributions, and extremes on the western and eastern slopes of the coast mountains. And training was super important as well. Training highly qualified personnel on the operation of state-of-the-art meteorological equipment, weather forecasting, storm monitoring, data analysis and interpretation, as well as remote fieldwork skills. So a lot of learning to be done. So here's a map of the study area for TRAIR. If you look at the top, at the center here, there's the Nechako watershed. That's the red outline. We're in Prince George here. And we were in this area, a little square, sort of the larger map here. Our 6 main field sites are the dots. We had Skins Lake Spillway. Huckleberry Mine was really our home base. Mount Sweeney, Medina River spawning channel. That's a Fisheries and Oceans Canada site. You see the Medina River on the right. We had some equipment in Terrace, and then some equipment at Camano as well. So on the left, you see at the top Medina. So I had the pleasure of staying in the Medina Lake Lodge for 2 months. But obviously this was for the field campaign and taking observations during storms. So that was an important component of being out there. It's just to be outside, and during storms, we were collecting information on conditions, including precipitation, winds, visibility, and we were doing that every 15 minutes. And of course, the storms can come at night just as much as during the day. So we're taking shifts and recording our observations. But as well, we had a number of instruments taking automatic information for us. So weather stations, the disdrometers, lake level loggers. So we had an instrument measuring the water level in Sweeney Lake here. So this is Huckleberry Mine. We had a whole suite of instruments there and along Mount Sweeney as well. We were recording water levels and water temperature in Ryan Creek and Whiting Creek, as well as other sites on the South Shore, the reservoir. And so a lot of instruments. In fact, we had 15 sites in total where we had some instrumentation in the vicinity of Huckleberry Mine. Okay, so just to provide you a little bit more of the visual perspective on these field sites. Rio Tinto was really helpful in providing us helicopter support to set up some instrumentation at Camano. They have a compound, as you see on the top left, with some instrumentation, and we were able to add a microwave radar and a laser disdrometer. On the picture, you see Hathaway Thompson, a former MSc student in my group at UNBC, who's now at UQAM, Université du Québec à Montréal, and Emile Cardinal, who's a master's student with Julie Thériault, and they're both working for Julie. And we're grateful to have the experience of coming to British Columbia and to participate in this field campaign. The center image is a weather station we have at Mount Sweeney. So this is 1,500 meters or so in elevation. Top right is Medina Lake Lodge, where, as you see, my dog Angel was participant as well in the field campaign. And we had not an automatic, but a standard rain gauge here that we would visit each morning and just record the amount of precipitation. And we were fortunate to have 2 volunteers as well at Jaslata Nation, having similar standard precipitation gauge and collecting data for us. That was super helpful as well in adding to our database of precipitation data. Bottom right is Skins Lake Spillway. So this had the Rio Tinto facility there, and we were able to set up a disdrometer and again, a microrain radar. And part of the idea is that when you move from the coast mountains onto the interior plateau, we're in the rain shadow now. So Skins Lake Spillway gets, 400, maybe 500 millimeters of precipitation annually, whereas in the mountains in the Tussa ranges, you get 2,000. So we wanted that gradient going from essentially sea level at Camano towards Huckleberry Mine, which is at high elevation, onto the plateau to get sort of that longitudinal profile in atmospheric conditions. Then we had weather station and the precipitation gauge at Medina River spawning channel. This was an interesting site to be in September and October, given all the grizzly bears. We had a lot of saké salmon coming up and spawning in the channel. So sometimes we had to turn back, and we were not able necessarily to go every day to visit our weather station, but it's their territory. So we had to respect them, and just beautiful to see, of course, all the grizzly bears feeding on the salmon there. And then finally at the bottom left is the UNBC campus and terrace. And again, we had some equipment that was borrowed from UQAM, a microrain radar, the dish that you see on the left. We also had a disdrometer and then a weather station from UNBC. So that was a great facility for us as well. All right, just to present a little bit of the data that we collected. And as I mentioned, during some of the storms, we were launching these, what we call radiosondes. So they're weather balloons with a little device. It's tiny and maybe 10 centimeters long, a couple centimeters in thickness. And we launched that using helium in the weather balloons. And we launched about 11 of these, typically before or during the storms. And then we collected data every second on air temperature, humidity, wind speed, wind direction, pressure. And we launched the balloons from Huckleberry Mine, and then we tracked them because we have a GPS receiver and we can track the weather balloons. In this case, this was October 15th, and you see that essentially the weather balloon launched from Huckleberry Mine and was transported from west to east, apologies, and the endpoint was actually towards François Lake, southeast of François Lake. And we caught some very strong winds in this event. So we caught the jet stream, and the wind speed maximum, as you see in the box, was 210 kilometers per hour. These balloons can go pretty high up to 15 kilometers. So they can actually reach the stratosphere. So it's pretty high up. So it takes a couple hours for them to reach that level. And eventually the balloon actually pops and will fall back towards the surface. Well, we did have a number of events during the Traer field campaign. In total, we had 11 major precipitation events. We had a lot of smaller events, but perhaps one of the major events was the 21st of September. And the red star indicates a study area. We see a map of Western Canada and the Pacific Northwest of the US. And the gray area indicates sort of a satellite image depicting clouds, and the color bar indicates the precipitation associated with those clouds. So you see again that elongated structure in the atmosphere. So that's our atmospheric river. It made landfall on Haida Gwaii and on the coast of BC near Prince Rupert, and was actually sort of traveling southeastward and carried a lot of moisture. We had precipitation rates per hour, that's the scale, of the order of 10 to 15 millimeters per hour during this event. So perhaps not good because there was some flooding in some areas, low-lying areas along the coast, but we were grateful in having this one atmospheric river actually make landfall in the vicinity of our study area. We did collect a lot of precipitation using, you see on the right, these tipping bucket rain gauges. They're self-logging, and we had about 6 of them actually deployed in the vicinity of Huckleberry Mine. Maybe we can just focus on the inset graph, where we focus on the period September 20th to September 23rd. And now we're looking at the cumulative precipitation over those 3 days. And of course, this is during that atmospheric river that occurred on the 21st of September. And you see the scale is in millimeters, starting at 0. And some of these precipitation gauges, we saw over 50 to close 60 millimeters of precipitation. So certainly nothing like compared to November 20 to 21 in southwestern BC, but certainly a lot of precipitation given we're inland from the coast. And certainly we were content to be able to get all of this data during an atmospheric river that made landfall in our study area. The other main plot just shows the cumulative precipitation at some of our gauges over those 2 months we were out for the Traer field campaign. And some of our sites, if you look at the very last numbers, we were recording 250 millimeters or so of precipitation. Well, as well, we wanted to look at the hydrological response in Whiting and Ryan Creeks. And we had essentially water level loggers, and these are essentially devices that measure the height of the water above a datum. And it was doing this every 15 minutes. We had water temperature data as well. I don't have a plot of that. And then finally, we had this flow tracker where we were out and taking measurements essentially every 10 centimeters across the cross section of one of the creeks. In this case, I think this is Whiting Creek. And that water was cold, by the way, 2 to 3 degrees at this time of the year. So it's pretty chilly, even with the equipment that you need to be out there in the water. So the plot on the left shows the water level, and you see a big spike on the 21st of September. So that's the atmospheric river that made landfall. So we're able to detect that in our water level data. We saw overnight essentially 40 centimeter increase in the water level of those 2 creeks. So again, important to have not only precipitation data, but hydrological data to see how the terrestrial response is to these landfalling atmospheric rivers. And of course, these creeks essentially drain into the Nechako Reservoir. So Rio Tinto is really particularly interested in not just the precipitation, but the water that flows into the reservoir. So it is possible later in the season that we saw additional atmospheric rivers and other major storms, but now it's getting colder. And so some of that precipitation will fall with snow. So you don't necessarily see as big a response as we saw on the 21st of September, which was a warm event. Essentially all the precipitation was falling as rain. Okay, some of the outcomes from our field campaign. And essentially, we had 11 participants, unfortunately more men than women. So in the future, we need to look into this and hopefully achieve gender parity in our team. We had a number of HQP, so research staff, master's students, PhD students, and a postdoc. We saw 250 millimeters of precipitation. This is at Huckleberry Mine, 11 storms in total. 2 were atmospheric rivers that made landfall in our study area. We had 3 other atmospheric rivers that made landfall to the north or to our south, and then 6 other storms. And then we launched 11 weather balloons. Collected a lot of data, as you see, 75 gigabytes of data. So we're all doing the quality control now. We had 59 field days in a total of 15 field sites. Well, we wanted to get some feedback from essentially the highly qualified personnel on their experiences. So here are some of the comments that we received. And I think this is really helpful in understanding what people actually learn through the field campaign. Again, training HKP was super important as a major objective from the field campaign. So some of the statements that we got were as follows: learning how to assemble, operate, download data, and decommission state-of-the-art meteorological equipment. That local topography plays a huge role in precipitation accumulation. Some people learned how to use what we call the tipping bucket rain gauge to measure precipitation air temperature, how to be safe in the wilderness, field safety protocols, being ready for all situations, and trusting your field partner. Connecting what I learned in classes for mountain meteorology to the mountainous environment people were observing firsthand. And for some, it was the first time taking discharge measurements. Although it was cold, I really enjoyed it. And importance of making sure your colleagues feel good, checking in with them, asking questions when doing remote or isolated field work, and then meeting researchers from different backgrounds and fields of expertise. So yeah, it was getting slightly cold by the end of our field campaign, but the advantage of doing this in September and October was no bugs. So that was a distinct advantage. Obviously, we had the bears to deal with, but no bugs. So what's next? Oh, there's a question. Maybe should we stop here for the question?
Yes, I'll read it, Stephen. It says,
Yeah.
question from Mike Nash.
Yes.
Any progress on making the radio sondes biodegradable? I have stumbled on 2 of them in the mountains so far.
Yeah, that's a very good question. And I'm not sure, but hopefully, they will, the suppliers, develop biodegradable radio sondes, including the weather balloons. So at this present time, I'm not aware of that, but hopefully people are thinking about this. Thankfully, they're not super large, but they would actually fall back towards the surface and end up wherever they fall. So that's a very good point. Yes. So in terms of the knowledge that we gained, so what's next? Well, we've collected a lot of data, and the data will be essentially analyzed by graduate students, postdoctoral fellows at UNBC, as well as UCAM. I see maybe there's another question now. Okay, yeah.
Yes, sorry. This question is from Audrey Faber, and it says, I also had a similar question regarding whether the weather balloons are recovered.
Yeah, at the present time, we're not able to recover them, but obviously if they're found, and I think there's a tag on them, if they are recovered, then they can be brought back to us and we can recycle them. Yeah. So we will be uploading our data to a public repository. So that's so that other people can actually use the data. And we're also in the process of developing a paper that will describe our data sets, and that will be submitted to an academic journal. As well, we'll be sharing our findings with a number of stakeholders. That includes Chislata Caribbean Nation and Rio Tinto. And in terms of the significance of this, ARs are predicted to become more intense and more frequent by the end of the 21st century across BC. So obviously it's important to understand this phenomenon. And then we'll be providing findings to Rio Tinto for their planning and operations in the Nechako Reservoir, particularly in the context of a future warmer climate in British Columbia. And perhaps we have another question.
Yes, we have a question from Mike Nash, and says the sondes that I found had a notice to the effect, please do not return to the weather office.
Oh, interesting. Okay. Yeah, that's interesting. Well, I'll have to look into that because I presume they must be recyclable in one way or another. I'll look into that. I'll contact some people at Environment Climate Change Canada. So they are the main people launching weather balloons, including in Prince George. There's a few sites across BC where they launch the weather balloons every 12 hours. So that's to meet a schedule globally to get vertical profiles of the atmosphere. And the data are super useful to initialize what we call the numerical weather prediction models, right? Yeah. Okay, so we're getting close to the end here. I just want to mention that we got a lot of attention in terms of the media for our trail field campaign. So we have a number of links here, and we have a website as well. You see the web link there. We also publish a quarterly newsletter as part of our program of research focused on the Nechako watershed. So if you'd like to be added to our mailing list, irc@unbc.ca is our mailing list, or email address, and we'll add you to the mailing list if you'd like to get that newsletter. It's also available through our website. And we post on social media. So I have an account on Twitter as well. Rio Tinto has been helpful in posting some information on Facebook. So a number of interviews that we did. So feel free to have a look at that. All right, so what's next? Well, we have another PhD student, Bruno Sobral. He's from Brazil, so it's been quite a transition coming from Brazil to study atmospheric rivers in British Columbia. He's focusing on the Nechako watershed and essentially the terrestrial response to these events. So that work is just getting started. We're also considering atmospheric rivers and hydrological modeling and water temperature analyses across the Nechako watershed. And as well, we'll be setting up some additional equipment to monitor atmospheric rivers and other extreme events in north central BC. And I have a slide about this, the Mesh Observatory with Dr. Judith Thériault at UQAM, as well as a potential new weather station at Chislada Lake with the Chislada Kara Nation. So an application was submitted just recently for that. So yeah, we're very pleased. Oh, sorry, there's another question.
Yes, the question is from Bruce Heslip. Ready stones are not recyclable. Current ones only a fraction of previous size. When balloons reach altitude, they usually burst into hundreds of little pieces.
Okay, good to know. Thank you, Bruce. So yeah, we're very pleased to announce the forthcoming creation of the Monitoring Extreme Climate and Hydrological Events Observatory, or MESH Observatory. It's a joint effort with UQAM. So Dr. Judith Thériault and I, with support from the Canada Foundation for Innovation, the Real Estate Foundation of British Columbia, and the BC Knowledge Development Fund. And the goal will be tracking and characterizing atmospheric rivers, hydrological and climate extremes in Western BC. And we'll have two major field sites, Terrace, so UNBC's Northwest Campus. You see the picture on the right. We actually started setting up some of this equipment last week. We had just beautiful weather for Terrace, beautiful, sunny, and we have a weather station that's now fully operational. And the benefit of having it at UNBC facility is we can actually use the internet network, UNBC network, and essentially we're transferring the data every 20 minutes back here to Prince George, and we can have a look at that. As well, we'll have equipment that will be set up at Tatsuneros at Huckleberry Mine. So two major field sites will have micro-rain radars, the laser disdrometers. We'll be acquiring some hydrological equipment as well. And we had a bit of a media release recently that was issued by UNBC. So there's more information with a video as well if you go to the link shown here.
We have a comment from Audrey Faber. It says, it'll be interesting to see the wind speed against the elevation profile from the weather balloon data you showed.
Yeah, absolutely. And this was just amazing to me that we were recording winds of over 200 kilometers per hour in some of our balloon launches. But yes, so we're able to look at the wind speed collected essentially every second and look at that profile of wind. So yeah, Audrey, that's something that would be interesting to focus on, absolutely. All right, so I think the next two slides are just some perspectives on what will happen in a future warmer world. So I think it's pretty clear that climate change is occurring. What will be the impact of atmospheric rivers? So this is a publication that came out in 2018. by Espinoza et al. And there's a color scale here which shows the change in the frequency of atmospheric rivers each year for the late 21st century relative to the late 20th century. So anything in red shows an increase in the frequency, anything in blue shows a decrease. So it's pretty clear that in a future warmer world, these atmospheric rivers are going to be more frequent. That includes, you might see the continent here in North America and British Columbia. So atmospheric rivers are not a new phenomenon, but we do anticipate that their frequency will increase and perhaps their intensity as well, because the air, as it gets warmer, can actually contain more moisture. And if it contains more moisture, there's the potential for additional precipitation formation. And what may be the impacts on rivers like the Fraser? So we obviously had that catastrophic flood in November 2021. And some of our work with the Pacific Climate Impacts Consortium had somewhat anticipated that's kind of flood in the Fraser. We were looking here at using a hydrological model forced by climate models and looking at the peak flow and the date of that peak flow for the Fraser River at Hope, BC. And on the left is our, what we call the historical period. So 1980 to 1989, the 1980s in green, the blue is 1990s, and the reds indicate the 2000s. And the horizontal line marks 1948, which was the last major flood for the Fraser River at Hope, with a flow of about 16,000 or so meters cubed per second. That's a lot of water coming through the Fraser. And the white box or rectangle indicates the period of the 1st of April to the 31st of July, which is typically the freshet, and when we experience, for the most part, the highest annual peak flow, according to our hydrological simulations forced by the climate models. A few events outside of that period, but mainly May through late July. On the right is what may happen in a future warmer world. And now you see that these high flow events are occurring pretty much across the entire calendar year. We have a lot more events in the fall and a lot more high flow events in the winter, and a reduction of the peak flows during that spring, what would be the typical spring freshet. And some of these high flows actually surpass that 1948 high flow of 16,000 meters cubed per second. So not only do we anticipate the change in terms of the timing of the high flows, but the intensity, we might see some events that will surpass the 1948 maximum of 16,000 meters cubed per second. So big changes ahead, and we've seen obviously, the destructive nature of the atmospheric river that made landfall in November 2021, but that's just potentially, what may happen again in the future, unfortunately. And we anticipate that some of these high flow events may be due to atmospheric rivers as well. So I think this brings my presentation to a conclusion. We have a lot of people to thank, and I just can't name them all, but I do want to mention the support of Rio Tinto, UNBC, and the Natural Sciences and Engineering Research Council for their financial support of the IRC program of research, in particular, the TRARE field campaign. But as you see, there's a lot of partners here from industry, from government, academic institutions. We have a number of First Nations that are supporting our research, and of course, some funding agencies. So I'll leave it at that. I just want to acknowledge members of my team, particularly Kelly Hurley, who was the TRARE project manager, and she worked so hard for the 1 year prior to the field campaign, and then the 2 months when we were out there in organizing, planning everything, every aspect of the field campaign. It took a lot of work. And she's now the research manager for my group. We had a a really incredible team in the field: Derek Gilbert, Anna Cavani, Selena Mitchell, Jeremy Morris, Bruno Sobral, and Jingweng Wu. And I think Asim Sharma, former PhD student in my group as well. And then the UCAM team that provided support: Emile Cardinal, Julie Thériault, Adley Thompson, and then a PhD student from McGill who are still participating in our field campaign, Pierrick Lamontagne Adé. So that is it. Thank you so much for your attention, and I'm happy to take additional questions, if any. Thanks so much. I think maybe Audrey has a question.
Yes, we have a comment from, let's see, from Bruce, and he's asking, do you know if high river flows have been correlated with deforestation? Correlate with deforestation, sorry.
Sorry, I did not get the question. Can you repeat that? Sorry.
Yes, it says, do you know if high river flows have been correlate with deforestation?
Yeah, that's certainly a major issue in the Nechako watershed. We've seen, just immense forest fires, including actually very near in Medina Lake Lodge. So that was a couple of years ago where we had a massive fire. And certainly we've seen perhaps more accumulation of snow and a faster snowmelt because of the loss of the canopy. So in the Nechako Reservoir, we've seen, I think, higher inflows just because of the change in land cover, in part due to the mountain pine beetle, forest fires. But these large floods, like the one in November 2021, are really due to heavy precipitation. There's a contribution maybe at the local or perhaps even the regional scale in terms of land cover changes, but really it's the amount of precipitation that falls in a short amount of time that's really the factor there.
Thank you, Stephen. And again, if you want to post a question, please use the Q&A speech bubble, and it's at the bottom of your screen. Catherine Nolan says, Stephen, such impressive field work, research, and training opportunities for UNBC students. Congratulations, and thank you for sharing with all of us. Our communities within the Nechako watershed requesting updates from you and your team?
Yeah, absolutely. And like I mentioned, we do published a quarterly newsletter, and we communicate with a number of First Nations as well. So we presented at chief and band councils and city councils as well. So we did actually a presentation to Terra City Council about a year ago. So yeah, there's a lot of interest on this phenomenon, and it's important to be able to communicate our findings to these communities. And there's no better way than doing that and just being in the field and meeting with people and talking to them. So we had, obviously, during the 2 months of the Trail Field campaign, a lot of opportunities to talk to people, including at the mine. So we invited people to actually watch the launch of a weather balloon, for instance. So it was a great, way to share the knowledge and how to launch, say, a weather balloon or the instruments that we were collecting data from. So we were able to show that to the individuals that were working at the mine. So yeah.
Thank you, Stephen. And we're going to give 1 or 2 more minutes for our audience if you have more questions. And we have one more. Audrey, she's saying, I am wondering if the Kitimat 2015 AR was an anomaly. Normally large snowfalls, there are at temps around -1 or -2 degrees with a warm up afterward, as happened in 1999. But in 2015, there were lower temps and it did not warm up. Rather, it was blizzard conditions with temps near Arctic outflows temperatures.
That's a very good question. It'd be interesting to look at the synoptic setup for that storm. So it's possible we had an Arctic air outflow coming from essentially northern British Columbia, northeastern British Columbia, cold air trap in the valleys, and then possibly this atmospheric river on top of it with warm air causing, it was cold enough for precipitation to fall as snow, but lots of moisture in that juicy air. So we haven't looked in that event in very much detail, Audrey, but it'd be interesting to see why there was so much snow, because typically these atmospheric rivers bring rain rather than snow. But having said that, we do see, some amazing snowfall events associated with atmospheric rivers. And I think the largest precipitation accumulation in terms of snow in Canada in 24 hours was at Tatsa Lake, 145 centimeters or so in one day. So yeah, some exceptional events that you can get along the coast, including in Kitimat and Terrace.
And we have one more question from Anonymous. Good presentation, Stephen. Did you find that higher elevation sites received more precipitation than lower elevation sites in the TRAIR study area for each atmospheric river?
Yeah, so that's another very good question. Certainly proximity to the coast was probably the most important aspect in terms of precipitation accumulation. The secondary factor would be elevation. Obviously, as you move up in elevation, you tend to have more of that, what we call the orographic enhancement. So indeed, the precipitation gauges that we're collecting near the alpine areas would be seeing more precipitation. So yes, that's correct. But again, proximity to the Pacific Ocean was the dominant factor in terms of the precipitation totals. The second one would be elevation. Yeah.
All right, we don't have any more questions. Anything you want to share with the audience?
I just want to thank everybody for attending the presentation. If you have any further questions, feel free to get in touch with me. My email address is sdery@unbc.ca, or you can reach us at irc@unbc.ca. Our website, we have updated results. And yeah, just thank you so much for attending the presentation this evening. Really appreciate it. Thanks for the opportunity, Carlos. Great to be part of this series of adult speaker presentations.
It was great having you. And one comment from Shiva, she says, such awesome work. Congrats to you and your team, Stephen.
Thank you so much. Really appreciate it. Yeah.
And
so now we need more storms.
Yes, interesting work. And well, I want to thank you, Stephen, for this amazing presentation. It was like full of knowledge and great information, basically. Thank you so much also for our media sponsors, CDC Daybreak North, and everyone who was able to join us tonight as well. Mm-hmm. And yes, just stay in touch, and we have like a lot of surprises coming up for the exploration place. And yes, we're having our reopening to the public on June 18th. So yes, just keep an eye on our social media and website. And yes, we'll have a bunch of surprises for everyone. Also, I have a final comment from Audrey, and she says, thanks, Stephen, great presentation, and thanks to the sponsors and host for holding another great talk.
Excellent, thank you.
Well, thank you so much, Audrey. And again, Stephen, thank you so much for being our host tonight. And yeah, great presentation.
Thank you so much. Have a wonderful evening.
Have a good night, everybody. And thank you for joining us.
Bye-bye.